Okay, welcome everyone. Thanks for joining for today's Pangeo Showcase. If this is your first time here, just as a brief orientation to this meeting, we start in the fall and spring seasons with showcase talks. These are really flexible in timing, but they usually go somewhere between 15 to 25 minutes. And then we turn off the recording and have open Q&A and discussion period that really lasts for however long people want it to. Usually, again, that's around 15 minutes or so. And then we go into the community meeting portion where anyone can share 60-second updates about what they've been working on or thinking about. And people who came for the showcase can stick around for that or head out, whichever they prefer. So let's get started with the showcase portion. So I'm really excited that Len Strnad joins us today. Len is a remote sensing and machine learning engineer with 7 years of experience in machine learning and 4 specializing in remote sensing. And over those 4 years, he has focused on simplifying the development of machine learning-based remote sensing applications, making them more composable, repeatable, and scalable. He's worked at Pachama modeling forest dynamics and perennial modeling soil organic carbon, both aimed at advancing carbon sequestration efforts. And his interests include uncertainty estimation for zonal statistics, leveraging the Pangeo software ecosystem to standardize and streamline data science operations, and scaling scientific computing with Flyte and UnionAI. And those interests are largely what he'll be presenting to us today. So thank you so much, Len. Really glad you're here, and please take it away.
Sounds good. Thanks, Max. Cool. Thanks, y'all, for joining. So today I will be talking about building scalable mosaic workflows with Flyte, Union, GDAL, and Xarray. So just a quick background about me. I think Max sort of gave me a nice intro, but I think I'll add on top of that saying that some of my motivations are typically to enable data scientists and advocate the usage of Pangeo Stack within various roles I've had on teams to standardize on different data models and compute standards and like Max said, that I've built a handful of end-to-end machine learning applications using workflow orchestration on top of a lot of the Pangeo stack, including Dask, Xarray, all these things on top of Flyte, which has been really, really good. I actually have 4 coworkers or ex-colleagues that are here today, so this might actually seem somewhat familiar to you all. You may or may not learn something today. Yeah, what else about me? I am not a contributor to a lot of the Pangeo stack, and I've always been eager to somehow give back. I'm always working behind closed doors at these startups, and so this is just one way to just demonstrate, or just one way to give back by just sort of giving a nice narrative of how, or a complete narrative of how how I've used a lot of the Pangeo stack. So hopefully it's helpful. Cool. So who are you? I wanted to establish some expectations and some assumptions around my audience a little bit. You may be a data engineer looking for a new orchestration tool. You may be a machine learning engineer looking for an orchestration tool to build end-to-end machine learning applications. You may be a scientist or researcher looking for a unified way to build experiments or data products. Or maybe use GDAL and want to see GDAL's GTI in action with Xarray, Flyte, and Dask. This is sort of what the talk is geared towards, and I'll probably be jumping around. I'll admit that this whole presentation has been put together since last night, so pardon any typos and inconsistencies. Cool. So on the agenda, I'll introduce a notion of standards for machine learning and remote sensing geared towards data models, compute, and mosaics for end-to-end applications. Then we'll introduce Flyte and particularly UnionAI. What's a task, what's a workflow, and what's the Dask plugin look like? Third, we'll review GDAL's various drivers for building mosaics, in particular the GTI driver. And finally, review example end-to-end mosaic workflow and all the caveats. So this is a bit ambitious. We'll see how far I actually get. So first, whenever I join a new team that is remote sensing, the first thing I try to do is establish some standards. And one of the three main standards is establishing a good data model for mosaics. So in remote sensing and machine learning, we are often working with data sets that look like what we see on the right here. This is basically an X-ray data set that has the schema that's more or less induced by like Rio X-ray. So if you were to open Rio X-ray, a TIFF in Rio X-ray with open raster.io, you're going to see a schema like something like this. You may have bands, X, Y, and then time is an additional variable that you typically won't see. But that is an additional dimension that is very common in a lot of machine learning needs. So basically the TLDR of this page is that Xarray is a really great candidate to model mosaic data sets and is a data structure that I have tried to standardize as inputs and outputs between workflow or orchestrations. It also allows engineers to inspect like intermediate artifacts in complicated workflows. So if you sort of agree on this data type part of the interface in each of your intermediate tasks or workflows, it makes it really easy for people to debug and inspect and use all the tools and all the functions that you get for free with Xarray. Now for compute, there are other things that I'm not going to touch on, obviously, but the two main things that I'm going to be discussing is use of Dask and the use of a workflow orchestration tool. Dask works really well for operations on Dask array-based Xarray operations, but has its limitations, as we are all very aware. And it's really great for a reasonable number of tasks that are short-lived, that are also reasonably sized and reasonably chunked. For example, like interpolating over time axis, for example, on an Xarray data set, maybe we want to try to reconstruct the underlying temporal signal. Workflow orchestration is helpful for repeatable, scalable version end-to-end applications. For example, one workflow to do ingest, pre-processing, train, predict, and then do final zonal stats in one fell swoop. This is something that these are the types of things that I often build is with workflow orchestration to sort of like streamline everything into one button, one entry point. One thing worth noting is that Dask is not a workflow orchestration tool, since each of these subflows can have varying compute needs, right? Like we might need way more compute for zonal stats than we may need for ingest, and it's really dynamic to launch up a different Dask cluster on each one of these tasks. So we want some way to sort of like unify this experience. So what is the ideal case? The ideal case would be like, let's combine the two. How can we use Dask and workflow orchestration together? What is another ideal thing that we would want? A quick iteration speed, infrastructure as code, intelligent retries, caching, writing everything in Python. These are all the things that you're going to get and more. And we'll chat about in a second here. So the last bit on standards, building mosaics in GDAL. So the assumption is like you have a list of analysis ready temporally stackable TIFFs for an AOI. And you have so many of them that building a single TIFF from command line with GDAL will not work in a reasonable amount of time. That's sort of our assumption here. And so we want to figure out a way to like actually scale it out. Another thing is that they may be in different coordinate reference systems. In that list of TIFFs, we might have 5 unique CRSs, and they're all going to potentially need to be reprojected and resampled to the final specified grid in order to give us something like, one unified Xarray data set on one final grid. There are also caveats. You might actually want to have one of these per CRS, but assuming that you want to actually reproject all of these TIFFs and potentially multiple CRSs into one final target grid. That's sort of like the focus use case of this talk. So there's some solutions with GDAL. You can do VRT, and then you can VRT for each CRS, unique CRS. You could build a VRT, then you could warp it to your target CRS. And then once you have all of those warped VRTs, you could then VRT all those VRTs and then have one final mosaic. And yes, you can open it with Rio Xarray, open raster.io, and specify chunks equals true to do it in delayed fashion. But there are caveats, which we'll get to later. And another approach, which uses a newer driver by GDAL, is GTI. You effectively build an index. You have a vector data set of all of the rosters, which is a bit mentally funny to get your head around. But once you do it, you start to see a lot of the convenience. And we'll dive into that a bit more in a sec. So what's the summary? In a lot of teams that I've worked on, establishing these standards has been really, really helpful. So let's unify workflows to operate on Xarray-based mosaics when possible. Let's use GDAL to standardize mosaic operations. And let's pick a workflow orchestration engine that enables these end-to-end applications, also experimentation, use of Dask, fast iteration, intelligent retry, caching version, infrastructure as code, and all these things. These are the things I try to build within all the teams that I work with in order to just streamline things. Okay, so now we're on to an introduction of Union and Flyte. So I've dropped a couple links here. You can go read for yourself all the documentation, but there is one important distinction. Flyte is not Union. UnionAI is not Flyte. UnionAI is a paid version of Flyte with all the bells and whistles. There are many extra features here that would not be possible in an unpaid version, and I highly recommend using UnionAI. It's been really great. I've been using it for the last 9 months. Getting up to speed and hitting the ground running has been amazing. They're super responsive. Their Slack channel engagement is awesome. They're very responsive to feature requests, and their polished UI is like very ergonomic with SSO and all this stuff. It's been fantastic. But you don't have to do paid version. Flyte is all open source. You can deploy it yourself. There's a great deployment guide, but there are always caveats with deploying things yourself. You may want a platform engineer to actually manage these things and roll out new releases with Helm. Or if you don't want to think about that at all, and you don't want to think about uptime and all these things, it's really, you're going to hit the ground running with UnionAI. I'm not working for them. I'm just a hype man. I really like the product that they have, so I'm just pushing it forward, saying like, hey, this is a tool I've used. It's worked really well. Consider using it. You've got some decisions to make. If you want to use Flyte as a orchestration tool, you can go through UnionAI or self-deployed. But even though I do not work for them, I did get a UnionAI cluster for this demo. Just want to highlight that I'm not affiliated with them. Cool. So I'm going to do a live demo. I'm going to jump right into it. And what I want to show is what a very, very basic workflow looks like. So in this example, we've got a task and a workflow. A workflow can operate on multiple tasks, and you can compose workflows in and of themselves. You can even pull them from across projects. But what we're gonna see here is one task that is just a Python function called add, and another workflow that's called add workflow. So what I want to demonstrate here is how quickly we can iterate, what infrastructure as code looks like, what interruptible, the support for interruptible, support for retries, all these things. And I want to show you how quickly you can iterate on these types of things. So first thing, I've made a make target to actually go register these things. I've already built an image that's being used as the latest image. You do have to build a container, and each of these tasks will be running these corresponding containers, but Flyte makes it really easy to register new code changes and actually go inject it into a container that you've already used. So if your dependencies haven't changed, you can do something like make a fast register. And all of the workflows, depending on how you specify things, will be registered as quickly as we're seeing here. Then we could go over to workflows and find this add workflow. This is what the Union UI looks like. It's going to be slightly different than if you were to deploy this yourself, but this is what I have right now. So this is what you get to see. And like I was saying, this UI is so ergonomic. I could spend a whole hour just talking about the features that are here, but I'm not here to sell UnionAI explicitly. We get natural support for different input types. This was inferred to be an integer, so we can for X and Y, so we can add their 2 bits, we can click launch, and we can see that the underlying task is being run. So, okay, fantastic. This is going to take a second because it's all built on Kubernetes. This is actually spinning up a pod on a cluster somewhere and running the underlying code that was just registered. And we can see that it has succeeded. We can inspect the outputs. We see that the inputs were 9 and 2, the outputs were 11 as expected. We can even go view the utilization that was used, all the task logs, all these things. We could rerun it in a debugger. It starts up a VS Code server, and then you can actually drop breakpoints and in places and actually debug this thing remotely, which has been amazing. But let's go back and just keep it simple. I don't want to spend too much time on these small examples here. But what I will show is like, maybe we want to actually cache this. Maybe we want to specify cache version. Let's set this to be interruptible. Well, let's not for now, because it might take a little extra to schedule. And then let's specify some resources. So this is what it would look like to enable caching for this task. So if the same X and same Ys are provided, Union or Flyte will go out to the database that manages all the caching. We'll check to see that X and Y have already been used for this particular function, for this particular cache version, and it will just forward the output. And will not actually rerun a whole, will not actually spin up a pod to check to see if that exists. It should be very, very quick. So we'll make that change, fast register, and you could probably, you can guess what's going to happen here. So registering, note that it takes a little bit longer because I'm actually registering like everything in this package. But you can actually register one specific workflow at a time. So if I relaunch this, I can refresh to get the newest version, which is right here. This was the version that was just launched, as you can see here. I can go launch it. We're gonna see that this task needs 1 CPU, 1 GB of memory. We can verify that by looking at this task once it actually runs. Where are you? It's in here, I promise. All right, so let's see. Caching was disabled. Add. All right, so if we rerun this again, caching should take place, and we should see that this doesn't actually run. Okay, it's not happening. This is a live demo. I don't know why it's not working. Don't worry about it. We'll just move on because I don't have that much time to spend on this component. Anyway, it does work. I use it all the time. It's fantastic. I love it. But standard demo things. Okie dokie, jumping back. So that's a very, very hyper quick, that's the 5-minute introduction of what Union and Flyte looks like. We're gonna move forward. Okay, now GDAL drivers and mosaics. There are a few ways that we can do this. We can do this with the GTI or with VRT, warp VRTs like we were mentioning before. The pros of taking a VRT, warp VRT approach is that yes, you can do Rio Xarray, open raster IO with your final .vrt with chunks equals true, and it's delayed. This is fantastic. It works well. You only need paths to the files, local or remote. You don't need any metadata. You don't need GeoParquet. You don't need stack parquet. You just need the path to the TIFFs. But what are the cons? GDAL build VRT needs to make a request to each file to get metadata, such as the transform, data type, number of bands, the no data, etc. And this can add up if you have like hundreds or thousands or tens of thousands or 100,000s or millions of files. Also, if you have heterogeneous CRS, you have to do this whole approach of first VRT the groups of TIFFs that correspond to one CRS. Then you have one mosaic. Then you warp it to your final CRS. And then you do that for each unique group of CRSs to actually build one final VRT. It's a bit cumbersome and it's not the most ergonomic. But the big thing for me, what I've noticed and I'm really excited about, is that this gets solved, this problem. If you already have all the metadata in advance, you can use GDAL's new GTI driver available in GDAL 3.9 and later. It does support heterogeneous CRS and tiles right out of the box. It indexes tiles in a vector format, which is a bit funky. Usually you think vector and you think roster data sets, but this is where they overlap. And it should also easily integrate in the future with Stack Parquet, which may or may not be happening today. I'm actually not paying that closely attention to Stack Parquet and integration with GTI. Some pros, if you have all this metadata associated with each tile, then you don't actually have to go make a request to 10,000 files or 100,000 files. Like that can take a really long time and can be prohibitive in a lot of cases. Building the VRT alone can take a very, very long time. It also supports connection strings. So in theory, it could take Zarr datasets, although I have not tried this. But this is something that could potentially be very, very cool if you use GTI to actually index Zarr datasets. And then you could kind of do the same exact thing, warp them all to the same CRS, mosaic a handful of Zarr datasets into one. It offers a lot of composability with mosaicing from various heterogeneous sources, which has been awesome. Cool. So now I have sort of very quickly whipped together a package that sort of demonstrates like a full end-to-end mosaic building workflow. Before I jump into this, Max, do you know approximately how much time I have left? 10? Is 10 minutes okay? I know we got started a little bit late.
That's totally fine.
Okay, cool. I will target 10 minutes. All right, so before we dive into that, I'm just going to go over a high-level summary of what this workflow achieves. We build one workflow that takes a bounding box, takes a set of dates, bounding box twice, and a data set. We'll see what a data set means in a second. And given this area that fully specifies the final mosaic that we want, ingest all of the required scenes as needed. Check if they exist. If they already exist, don't need to go get them. Build feature level cogs as needed. If they exist, we don't need to go rebuild them. Build GTI index per datetime. And each one of those is going to correspond to a temporal slice within an Xarray data set. And then build a target data set with 2Zarr, specifying the store and compute equals false to get all the metadata there. And then we're going to write each partition of chunks to this region. This should be 2Zarr with the particular region in mind. This is something that I had found on Pangeo Discord a while back, not Discord, Discourse a while back. Was, you know, what if the target mosaic is like much too large to just say, hey, Dask cluster, like 2Zarr this for me. This could just blow up, right? Like if you have so many Dask chunks where you're submitting like 500,000 tasks at once, you need a way to maybe submit these things in serial in a way that like isn't going to overwhelm the scheduler. And you know, maybe a lot of really exciting things like Cube are going to be able to solve this. But I've also seen issues like you know, workers running out of memory, tasks retrying more than the number of tolerated times. And what we try to do is bypass this by actually partitioning chunks themselves. So I iterate over chunks of chunks, integer multiple of chunks to submit large batches at a time in serial in order to bypass this issue. And it's worked really well for me. Okay, cool. So where should we start? Given we have 5 minutes, let's start at build. So basically what I'm going to show you is what some of these workflows look like. And I'm just going to sort of like read through the semantic story of the workflow that accomplishes this end to end. So we've got a workflow. It's called, and we're going to go see the counterpart over on UnionAI. We're going to go inspect the underlying tasks and see some of the inputs and outputs. So I have one workflow. It's called Build Dataset Mosaic Workflow. This might be something a data scientist is like, hey, this already exists. I need to go build a really large Xarray mosaic for this particular data set at this particular resolution in this CRS. with this particular chunk size for these times for this region. And what these types of work will enable is for data scientists to come self-serve, um, uh, building a really large Zarr-backed Xarray mosaic for any of their future experimentation, or maybe this plugs into a full end-to-end machine learning pipeline where we have sort of fused a few data sets together, and those are now our covariates inputs to our model. We apply a model, and the output again is another Xarray mosaic, sort of standardizing on this data model between inputs and outputs of these workflows. So that's sort of the idea around why we're building this single workflow is to serve all these different use cases. But let's just read this semantically. So first thing, we go ingest all the scenes. Then we go build scene features. So in this particular case, the only implemented data set that I have right now is this GLAD ARD mean. So basically what I've done here is used dataset enums to enumerate all the possible data sets that are there. And I go implement this protocol that basically says like, hey, what's all the metadata that I need for this particular data set? What are the bands? What's the temporal window? What's the earliest, latest? What's the date type of the final product? And also, what is the underlying scene protocol? Well, the scene protocol, we'll sort of back up. The scene protocol, this is like the class that's responsible for knowing what are all the underlying scenes that are going to be needed in order to take the annual median. So given the bounding box and given the temporal range, it's going to go get all the scenes that would be required for this particular date type's annual median composition. And so backing up to build here, this is going to provide a GeoPandas data frame that indexes all the scenes. And this is going to actually go say, okay, you said to go build a mean-based X-ray data set. I know exactly what scenes I need. I'm going to load all those scenes, persist them out locally to Zarr, and then I'm going to call .mean, and then I'm going to write it out to cog. So both of these, the scenes that are downloaded are converted to cog. The scene features that are built are converted to cog. And what this allows us to do, why I always take this approach, is to basically only ingest things on an as-needed basis. So we sort of build and accumulate a tile feature cache of things as we need it over time. And if you have already ingested things, then these workflows should just rip. They should totally fly. And then we're left to go build GTI, go build our GTIs, and then go build a target mosaic, like we were saying, with two Zarr compute equals false, and then go write each of those partitions in parallel using Flyte's map task. That's sort of, this is one way to go about parallelizing these things. I'm realizing that I've got 2 more hours worth of things to talk about, but I've got about 3 minutes left. So I'm going to try and wrap it up here. I'm first going to jump back to the UnionAI just to demonstrate what this looks like. And then I'm just going to talk about caveats, and then we'll close things up. So the build dataset workflow, you can see how many failures I've had since the 12th, which is, I think, this morning or yesterday. But we do have one successful workflow that demonstrates this whole thing end to end. First, we'll view what the inputs and outputs look like, or what it looks like to launch this thing. This could have probably been set to a reasonable default. This is saying let's build chunks such that integer multiple of chunks such that we have about 2 gigabytes per partition. Here's an AOI of our area of interest in EPSG 4326. This is the resolution I'd like to specify. Here are the dates I want that correspond to my final features. This is going to be the final chunk size of the target data set. And enums are nicely supported in Flyte, where I get to drop down and select that one data set that I actually implemented. So if I go launch this, what we'll see is that, for ingesting scenes workflow, we get all the required scenes. We determine the ones that need to ingest if they don't exist. We partition the geodata frame into chunks. And And then we use we use map task to actually map over chunks of each of those data frames to go actually download all of those corresponding URLs. Then we finally build the expected scenes GDF, and we have a nice overview of what this thing looks like. So we have basically date, time, and then the S3 path to where these things live. So that's the scene. That's scenes. Now for building the scene features, this is going to be on a tile by tile basis for each time. Go get all the scenes that we need, compute the mean, store it out to cog, and then we'll reference those cogs when we go build our GTI to build our mosaic. So we're doing very similar things here. You'll see that I like to use GeoPandas data frames everywhere to sort of index a lot of these assets. And yeah, and people may or may not like that. I think people who are very, very strict on typing are going to be like, how do you even know what the schema is? And there are nice things like Pandas we could use to actually validate schemas and things, and I've yet to implement that, but it's definitely something that I appreciate. Cool. Just to wrap up this workflow, we build a GTI. We do that per date. So we have two because we only have 2 date times. Then we go build the target mosaic. I don't think the target mosaic looks like this. So it's actually not that big. I know this is all about building scalable Xarray data sets. I promise that this type of approach has worked for data sets up to multiple tens of terabytes for me. And I think at some point, you can always break every system by just either cranking the resolution all the way down or cranking the extent all the way up or cranking the temporal grid up resolution as well. You can always break these things, I feel like, but cool. And then the final thing is like mapping these so for each GTI, for each partition of these chunks, we then go read that corresponding GTI. We slice out the region, we call compute, and we write it to Zarr, that particular region. So yeah, that's what the workflow looks like. And the last thing will be caveats. And Max, do you mind if I have two more minutes? Is that okay? Or should
Yeah, please don't rush. You're good.
Okay, cool. Okie doke. So for caveats, there's a lot. There's a lot going on. I know I wasn't able to really step too deeply into exactly how I implemented these things. I really tried to put things up on GitHub so that you could take a look at how some of these things are implemented. Please feel free to leave issues to open discussions if you are asking hey, why did you implement things this way or that way? It's not intended to be, an open source package that people are going to use. More or less just try to get some ideas out there of how to implement this or one way to implement things. Okay, so yeah, so for caveats, when I'm actually building the final feature cog, I persist it out to Zarr locally in order to actually make things happen reliably. What's happening is that I'm doing raster.io read Rust for each TIFF, and then I'm concatenating it along the time axis. And if I keep doing that thing in a delayed fashion, too many tasks end up just blowing things up. I run them into memory errors. So I've decided to, when getting all of the required scenes for that one particular feature cog, persist it all to Zarr as an intermediate step, and that makes things a lot more reliable. Checking if files exist every time is not very scalable. We might actually want to plug in stack or something like this to go check to see if we've already ingested things. But right now, I'm actually checking to see if every single file exists, and that's going to blow up as soon as we get into the realms of millions of TIFFs, millions of files. Flyte's map task also prefers less than 10,000 tasks, and just like Dask, Flyte also has its number of tasks concern. So you always want to be very careful about choosing the number of chunks, but also choosing the partition size of the chunks to ensure that map task doesn't blow up and the underlying Dask doesn't blow up. When using Dask plugin, which was implemented by one of the members of the audience, code needs to be in a container. So if you make a change to underlying code, that actually has to be in the container. So just like you might be used to, possibly with coiled, I'm not totally sure, or in other circumstances, if you're using a Dask cluster in a remote setting, your code needs to be in your container and you need some way to get in there. So that might involve actually building a container and pushing up and re-referencing that new image. We partition chunks and integer multiples to submit work to keep the amount of work, the amount of memory usage limited. GDALs, a GTI driver is sticky. So if you try to concatenate, if you use one GDAL per time and then concatenate over the time axis and call compute, you're actually going to get the most recent one repeated over the time axis. So there are ways to work around that, and that I've implemented in the project that I shared. GDAL has recommended specific metadata, and basically this is the metadata that will allow it to not have to go make a request to any of the underlying files that you have. I found that it definitely speeds things up if you provide all of that metadata, like the data type, bounds, resx, resy, things of that nature. Also, GDAL configs matters a lot. Um, I have a section that applies some heuristics based on the size of your worker to configure the GDAL config. You can go check it out at your convenience, but effectively, you may get some blob contention if GDAL isn't building an effective cache. And sometimes I found that using Dask single-threaded executor, but with GDAL number of threads as all CPUs helps build a more meaningful GDAL cache so that when you hit the next chunk over, it's likely to overlap a cog or an underlying block that was already needed for the previous. And that ends up speeding things up significantly. Yeah, and there's so many ways to parallelize. Like we can use local Dask, we can use a Dask cluster, we can use map task and Flyte, and any combinations thereof. And I found that, you know, just being equipped with these things is really nice and makes it really easy to like scale things out arbitrarily for really large Xarray mosaic data sets. So yeah, that's the end of my talk. I hope that it was somewhat cohesive and was able to give you sort of a lay of the land of how I've been able to build scalable end-to-end mosaics all the way from ingestion to like analysis ready Xarray data sets. Thanks for attending.
Thanks, Len. That was really awesome.